What if the universe wasn't the vast, empty, and disconnected place it appears to be? What if every single particle, every star in a distant galaxy, and every neuron firing in your own brain were all instantly, irrevocably linked? This isn't a premise from a science fiction novel, but a stunning reality revealed by one of the most mind-bending principles in all of physics, non-locality. It's a concept that shatters our most basic assumptions about space and time, suggesting a hidden layer of connection that weaves through the entire cosmos. Think about the sheer scale of the universe for a moment. We look up at the night sky and see immense distances, a void so enormous that light itself takes billions of years to cross it. We feel separate, a tiny speck in an indifferent expanse. But what if that feeling of isolation is the greatest illusion of all? Non-locality proposes that beneath the surface of reality, there exists an immediate, intimate link between things, no matter how far apart they seem. It challenges not just what we see, but how we define existence itself, turning the cosmos from a collection of lonely islands into a single, interconnected whole. This journey we're about to take together explores one of the most profound and humbling ideas humanity has ever encountered. We're going to unpack the science that points toward this incredible interconnectedness, from the strange behavior of tiny particles to the implications for consciousness and our place in the grand scheme of things. It's a story of human curiosity pushing against the limits of understanding, a quest to see the universe not as a cold, mechanical clockwork, but as a living, breathing tapestry where every thread is essential to the whole. So get ready to have your perception of reality gently turned inside out, as we explore the fascinating evidence that everything, everywhere might be instantly connected. To really grasp this idea, we first need to understand the world we think we live in. Our everyday experience is what physicists call a local reality. In this view, objects are only influenced by their immediate surroundings. If you throw a rock into a pond, the ripples spread out from that point, affecting the water nearest to them first. If you want to talk to a friend across the planet, your message has to travel whether as a radio wave, a fiber optic signal, or a letter in the mail. It takes time. Nothing, according to this common sense view, can have an instantaneous effect on something far away. The speed of light is the universe's ultimate speed limit, and information or influence simply cannot break that rule. This local reality feels solid, predictable, and logically consistent with everything we see around us. But in the 1930s, a thought experiment emerged that would challenge this very foundation, creating a puzzle that even the greatest minds of the era struggled to solve. Albert Einstein, along with his colleagues Boris Podolsky and Nathan Rosen, devised what is now known as the EPR paradox. They weren't trying to prove that the universe was strange. In fact, they were trying to show that the then new theory of quantum mechanics must be incomplete. They argued that if quantum theory were correct, it would lead to a seemingly absurd conclusion. Two particles that had once interacted could become entangled, their fates linked in such a way that measuring a property of one particle, like its spin or polarization, would instantly determine the property of the other, even if it was now light years away. To Einstein, this was unacceptable. It implied a mysterious, instantaneous connection that violated the local realism he held dear. He famously dismissed this bizarre implication as spooky action at a distance, believing it was proof that a deeper, more complete theory must be waiting to be discovered. What Einstein saw as a fatal flaw, however, turned out to be a fundamental feature of our universe. Decades later, experiments by scientists like John Stuart Bell and Elaine Aspect provided stunning confirmation that this spooky action was real. When two particles are entangled, they don't just share a common history. They behave as a single, unified system regardless of the space between them. Measuring one does not send a signal to the other. There is no travel time. The change is simply simultaneous. It's as if you had a pair of magical dice, one in your hand and the other on a planet orbiting a star in a distant galaxy. The moment you roll your die and it comes up a 6, you know with absolute certainty that the die light years away has also, at that exact same instant, come up a 6. This connection defies our deepest intuitions about cause and effect and seems to ignore the cosmic speed limit set by light itself. This isn't just a theoretical curiosity confined to a laboratory. It's a property that is actively used in emerging technologies like quantum computing and ultra-secure quantum encryption. The universe, it appears, has a hidden, deeply interconnected layer, a non-local reality operating just beneath the surface of the world we perceive. For decades after Einstein's objection, this debate over spooky action remained a philosophical stalemate, a war of ideas without a battlefield. The scientific community was divided, with no clear way to determine whether Einstein's local realism or the bizarre quantum connection was the true description of our world. The impasse seemed unbreakable until an unassuming physicist at the European Organization for Nuclear Research, John Stuart Bell, had a monumental insight in the 1960s. Bell wasn't conducting a flashy experiment. He was working with pencil and paper, probing the deep mathematical structure of quantum theory. What he produced was a theorem of breathtaking elegance and power, a conceptual tool that could, for the first time, settle the argument through experimental evidence. At the heart of his work was something now known as Bell's inequality. Think of it not as a complex equation, but as a cosmic litmus test. It established a strict mathematical limit, a boundary line for how correlated the results of measurements on two separated particles could be if the universe truly operated on the principles of local realism that Einstein championed. In a locally real world where particles have definite properties before we measure them and no influence can travel faster than light, the correlation between measurements would always have to fall below a certain threshold. It's like having two people in separate rooms, each flipping a coin. If the coins are ordinary and there's no hidden communication, the number of times they both get heads will have a predictable, limited maximum. But Bell's math showed that quantum mechanics predicted something very different. If the particles were truly entangled, their correlations would violate this inequality. They would be stronger, more synchronized than any locally real hidden variable theory could possibly allow. It would be as if our two coin flippers, with no way to signal each other, were somehow matching their results far more often than pure chance could explain. This was the breakthrough. Bell had transformed a philosophical debate into an experimental question. He provided a clear, testable prediction. If you perform a specific experiment and the results violate Bell's inequality, then Einstein's comforting view of a local and deterministic universe cannot be correct. The universe would have to be either not local, meaning influences can indeed connect distant points instantly, or not real, meaning particles do not have definite properties until they are measured, or perhaps, and most mind-bogglingly, both. The stage was now set for a series of historic experiments, most notably by Elaine Aspect and his team in the 1980s. They created pairs of entangled photons and sent them flying off in opposite directions to detectors several meters apart. At the very last moment, as the photons were in flight, they would randomly change the settings of the measuring devices. This crucial detail prevented any conceivable signal traveling at the speed of light from coordinating the particles' responses. The results were unequivocal. The measured correlations between the entangled photons did not just slightly exceed Bell's limit, they smashed through it. The data aligned perfectly with the predictions of quantum mechanics, delivering a powerful verdict against local realism. John Stuart Bell's theoretical work had been spectacularly confirmed. This was not a minor adjustment to physics, it was a tectonic shift in our understanding of reality. The Bell theorem breakthrough forced us to accept that our universe is fundamentally non-local. The spooky action that Einstein so vehemently rejected is an integral, inescapable part of how the cosmos operates. The work of a quiet theorist had forever changed the landscape of physics, proving that the connections weaving through reality are far more mysterious and profound than we ever imagined. So with Bell's theorem providing a clear experimental target, the race was on to actually perform the test. The challenge was immense. To truly rule out any possibility of a hidden, slower-than-light signal coordinating the particles, the experiment had to be nearly flawless. It needed to ensure that the choice of what to measure on one particle was made after it was physically impossible for any signal, even at the speed of light, to reach its entangled partner and tell it how to behave. This was the monumental task that a young French physicist, Alain Aspect, and his team undertook in the early 1980s. Their laboratory setup was a masterpiece of ingenuity. They began by creating pairs of entangled photons, which are particles of light. They did this using a special process where they excited calcium atoms with lasers, causing them to emit two photons that were inherently linked, their polarizations entangled. These photon pairs were then sent flying off in opposite directions down long vacuum tubes towards detectors positioned several meters apart. Now, here was the brilliant, critical part of the experiment. Each photon on its journey would reach a switch that could rapidly and randomly direct it to one of two different polarizers devices that measure the photon's polarization in a specific orientation. The genius of Aspect's design was the speed and randomness of these switches. The setting for each measurement, the direction in which the polarizer was aligned, was changed while the photons were already in flight. This is the crucial detail, because the distance between the switches was greater than the distance light could travel in the time it took for the switch to change. It became physically impossible for any information about the measurement setting on one side to reach the other photon before its own measurement was completed. It effectively cut off any conceivable, secret communication channel between the two particles that obeyed the cosmic speed limit. The team then recorded the results over thousands of trials, noting whether each photon passed through its polarizer or was blocked, and then compared the outcomes from the two separated detectors. In a locally real universe, as defined by Bell's inequality, the correlation between these results should have stayed below a strict threshold, but that is not what the data showed. The correlation between the entangled photons was significantly stronger. It violated Bell's inequality, and it did so in a way that perfectly matched the predictions of quantum mechanics. The photons were behaving as a single, unified system, their fates intertwined across space in a way that defied any local explanation. Aspect's experiments were a watershed moment. They didn't just suggest that quantum mechanics was correct, they provided powerful, direct evidence that the universe is fundamentally non-local. The spooky action at a distance was not a philosophical idea or a mathematical curiosity. It was a concrete, measurable physical phenomenon. This work, for which Aspect would later share the Nobel Prize in Physics, slammed the door on Einstein's hope for a local hidden variable theory. It forced the scientific community to accept a profound and uncomfortable truth, that our intuitive understanding of space as a separator is at a fundamental level an illusion. And this brings us to the heart of the mystery, the phenomenon of entanglement itself. If we strip away the complex mathematics, what we are left with is perhaps one of the most beautiful and strange relationships in all of nature. It's a cosmic love story written into the fabric of reality. Picture this: two particles are born from the same event, emerging into existence at the exact same moment. From that instant, they are bound together, their identities fused into a single, shared quantum state. They are like a pair of cosmic twins created together and then sent flying off into the universe in opposite directions. And no matter how vast the distance between them grows across a laboratory table or across the unfathomable gulf between galaxies, their connection remains unbroken. They are forever a single system, a unified entity that just happens to occupy two distinct locations in space. This is where the magical dice analogy becomes so powerful. Imagine you have two dice that were created as a pair, entangled at their birth. You keep one die and you send the other on a journey to the farthest star you can imagine. Now you roll your die here on Earth. It tumbles and bounces and finally comes to rest, showing a 3. At that precise moment, without any signal or communication, the die at that distant star also settles and it too shows a 3. Every single time you roll your die, the outcome of its partner is instantly determined. It's not that the dice are communicating, it's that their fates were never truly separate to begin with. They are two parts of a whole, and the act of observing one part instantly defines the state of the other. This isn't just a theoretical fancy, it's precisely how entangled particles behave. They share a common identity, and measuring a property like the spin or polarization of one particle doesn't just tell you something about its partner. It actually defines what that property is for the partner, locking it into place across any distance. The universe, it seems, doesn't tally up the individual states of these far-flung particles until the very moment we look at one of them. It's as if the cosmos is holding all the possibilities in a state of shimmering potential, and our act of observation is what forces a single, concrete reality to snap into focus everywhere at once. This quantum bond forces us to reconsider what we mean by separate. Two things can be physically distant, yet remain intimately and instantaneously linked in a way that our classical minds struggle to comprehend, revealing a layer of unity that underlies the apparent separateness of our world. Now, this is where things get really tricky for our intuition, because we've just described a connection that seems to act instantly across any distance. And for over a century, we've been taught one of the most fundamental rules of the cosmos. Nothing, absolutely nothing, can travel faster than the speed of light. It's the universe's ultimate speed limit, a cornerstone of Einstein's theory of relativity that has been verified again and again. So how can both of these things be true? How can entanglement be instantaneous without breaking the most sacred rule in physics? This is the central paradox, and resolving it requires us to make a subtle but absolutely critical distinction. The key is to understand that in these experiments, no thing is actually moving between the entangled particles. No signal is being sent, no message is being transmitted. No particle of matter or burst of energy is making the journey. Think back to our pair of magical dice. When you roll your die and see a 3, you instantly know that the other die is also showing a 3. But did you send a command to it? Did you somehow beam the number 3 across the galaxy? No. The correlation, the fact that the two dice always match, was established the moment they were created as a pair. That relationship was baked in from the very beginning. The act of you rolling your die and looking at it doesn't change the distant die. It simply reveals a fact about it that was always true, a fact that was an inherent part of their shared history. This is the core of the matter. What appears to be a transfer of information is actually just the unveiling of a pre-existing correlation. The universe, in its deepest quantum description, allows for these kinds of global correlations that don't rely on sending signals through space. They are more like two sides of the same coin. Flipping one side to heads doesn't cause the other side to become tails. It was always the other side of that same coin. The correlation is a single, unified property of the system, not a message sent between its parts. This is why physicists carefully state that while the correlation is instantaneous, it cannot be used to send any meaningful, controllable information faster than light. You can't use entanglement to call up a friend on another planet. Why? Because the outcome of your measurement is completely random. You have no control over whether your particle will have spin up or down. All you know is that whatever random result you get, your friend will get the correlated result. But until your friend actually looks at their own particle, they have no idea what state it's in. And until you compare notes through a conventional, slower-than-light channel like a radio transmission, neither of you can even detect that this spooky correlation has occurred. So causality, the principle that cause must precede effect, remains perfectly intact. No one can use this phenomenon to create a paradox, like sending a message back in time to prevent their own birth. The cosmic speed limit for sending usable information or moving matter is never broken. It's preserved, but at the cost of revealing a universe that is far more deeply and strangely interconnected than we ever thought possible. The connection of entanglement seems to exist in a realm that operates outside our everyday understanding of space and time, a foundational layer of reality where what we perceive as separate objects are still fundamentally one. But if no signal is traveling and no information is being sent, what is really happening during that instantaneous correlation? One of the most audacious and compelling answers comes from a different interpretation of quantum mechanics altogether, an idea that reimagines the very nature of reality to explain this strangeness. This is the many worlds interpretation proposed by physicist Hugh Everett in the 1950s. It offers a breathtakingly elegant, if almost unimaginable, solution to the puzzle of non-locality. The core of Everett's idea is deceptively simple. The universe we experience is not the only one. Instead, every time a quantum event occurs with multiple possible outcomes, like the spin of an entangled particle being measured as either up or down, the entire universe doesn't just choose one outcome. It splits or branches into multiple, equally real versions of itself. In one branch, the particle is measured as up, and in another parallel branch, it is measured as down. And this happens for every single quantum event, constantly and ceaselessly, creating an ever-branching tree of parallel realities, a multiverse of staggering proportions. So let's apply this to our pair of entangled particles. When they are created, they are a single, unified system. But the moment you go to measure one of them, the universe is faced with a choice. According to many worlds, it doesn't make a choice. Instead, it splits. In one new branch of reality, you measure particle A as up, and because they are entangled, particle B is instantly down. In the new parallel branch that splits off at that exact same moment, a different version of you measures particle A as down and particle B is therefore up. From this perspective, the spooky action at a distance completely vanishes. There is no mysterious instantaneous influence reaching across space. What we perceive as a sudden, faster-than-light connection is actually just a pre-existing correlation being revealed within our own branch of the multiverse. The two particles weren't communicating. They were always correlated across all possible branches from the moment of their creation. Your act of measurement didn't cause the distant particle to snap into a state. It simply determined which branch of reality you, the observer, now find yourself in. The eerie synchronization is just a consequence of the fact that in your specific universe, the two outcomes were always locked together. This framework elegantly preserves locality, as no influence needs to travel between the particles, and it also preserves realism, as the particles have definite states in every branch. The cost, of course, is accepting that reality is wildly, exponentially more vast than we ever supposed, with every possible outcome of every quantum interaction playing out somewhere. It suggests that the interconnectedness we see in entanglement is not a connection through space, but a connection across the unimaginably vast landscape of parallel worlds, a cosmic tapestry woven from every possibility. While the story of entangled particles is profound, it only scratches the surface of this cosmic interconnectedness. To truly appreciate the scale, we need to zoom out from individual particles to the very fabric of spacetime itself, entering the domain of quantum field theory. This framework, which combines quantum mechanics with special relativity, doesn't just describe the universe as being made of tiny, separate billiard balls. Instead, it paints a picture where the fundamental ingredients of reality are fluid, dynamic fields that permeate all of space. Think of the entire cosmos as an immense, invisible ocean. An electron is not just a solitary particle, but rather a localized excitation, a kind of persistent ripple or wave in a universal electron field. There's a field for every fundamental particle, a quark field, a photon field, and these fields are everywhere, stretching across the universe. What we perceive as empty space, the vacuum, is not a barren nothingness. According to quantum field theory, the vacuum is a seething, bubbling cauldron of activity. It is the lowest energy state of these fields, but lowest doesn't mean inactive. Due to the inherent uncertainty of quantum mechanics, the fields are constantly fluctuating. This gives rise to what we call virtual particles, pairs of particles and antiparticles that spontaneously pop into existence from the vacuum, borrow energy for a fleeting moment, and then annihilate each other, returning the energy back to the field. This isn't just theoretical, it's a measurable effect with real-world consequences, such as the Casimir effect, where two metal plates placed extremely close together in a vacuum are gently pushed toward each other by the pressure of these virtual particles fluctuating outside them. This vibrant vacuum is the true ground state of the universe, and it is fundamentally non-local. The fields themselves are not confined to points in space. They are extended entities, and their quantum states can be entangled across vast distances. The virtual particles that blink in and out of existence are often born in entangled pairs. Their brief lives a microcosm of the same spooky connection we see in laboratory experiments. This means the non-locality we discovered with particles isn't an exception or a rare curiosity. It is woven directly into the substrate of reality. The empty space between stars, the void between galaxies, is not a cold, dead separator. It is a living, dynamic medium humming with non-local connections. The entire cosmos is underpinned by this quantum field fabric, a seamless tapestry where every point is instantly and intrinsically linked to every other point through these vibrating fields. This perspective elevates non-locality from a strange property of particles to a foundational principle of the universe. The interconnectedness isn't something that happens in space. It is a property of space, or more accurately, of the fields that constitute space and everything in it. This journey into non-locality takes an even more dramatic turn when we venture into the most extreme environments in the cosmos, black holes. These mysterious objects where gravity is so intense that not even light can escape, present one of the greatest puzzles in modern physics, a puzzle where non-locality might just hold the key. The story begins with Stephen Hawking's groundbreaking work in the 1970s. Hawking realized that black holes aren't completely black. By applying quantum field theory to the curved space-time around a black hole's event horizon, the point of no return, he made a stunning prediction. The intense gravitational field can cause pairs of virtual particles to pop out of the vacuum, just as they do everywhere in space. Normally, these particle-antiparticle pairs annihilate each other almost instantly. But at the event horizon, something extraordinary can happen. One particle of the pair might fall into the black hole while the other escapes into space. The particle that escapes carries away a tiny amount of energy, and to conserve energy, the black hole itself must lose a correspondingly tiny bit of mass. This stream of escaping particles is what we call Hawking radiation. Over immense stretches of time, this process causes the black hole to slowly evaporate, eventually vanishing entirely. This was a monumental discovery, linking quantum mechanics, gravity, and thermodynamics in a way no one had ever done before. But it created a massive problem, one that has haunted physicists for decades: the black hole information paradox. In quantum mechanics, information is never truly lost. The quantum state of a system, the precise information about every particle that fell into the black hole, must, in principle, be preserved. It can be scrambled and transformed, but it cannot be erased. If you burn a book, the information in its pages isn't really gone. It's just converted into a vastly more complex state in the smoke and ashes. In theory, with a perfect understanding of physics, you could reverse the process and reconstruct the book. But Hawking's original calculation suggested that the radiation escaping a black hole is purely thermal, like the heat from a stove. It's random and featureless, containing no information whatsoever about what fell in. So, when the black hole finally evaporates and disappears, what happens to all that information? According to this view, it would be permanently erased from the universe, violating a fundamental tenet of quantum theory. This is the core of the paradox, a direct conflict between general relativity and quantum mechanics. For years, this seemed like an intractable problem, but this is precisely where the concept of non-locality offers a compelling solution. The key insight is that the pair of virtual particles responsible for Hawking radiation are created from the quantum vacuum, and like the entangled particles we've discussed, they are born in an entangled state. One falls in, the other escapes. For the mathematics to work out consistently, the entanglement between the escaping Hawking particle and its infalling partner must be transferred. As the black hole evaporates, the escaping radiation must somehow remain entangled with the interior of the black hole, and ultimately with the radiation that escaped earlier in the process. This creates a web of complex, non-local connections that transcend the event horizon. The event horizon, in our classical understanding, is an absolute barrier. But quantum non-locality suggests that information doesn't need to travel across the horizon. It is preserved through these instantaneous correlations that link the inside and the outside. This leads to a truly mind-bending idea, often described in the context of the holographic principle. The holographic principle proposes that all the information describing a three-dimensional volume of space, like the interior of a black hole, can be entirely encoded on its two-dimensional boundary, the event horizon. It's like a cosmic hologram where a three-dimensional image is stored on a flat, two-dimensional surface. In this view, the information about every star, planet, or molecule that falls into a black hole isn't lost inside the singularity. Instead, it is non-locally smeared and stored on the event horizon itself. Then, as the black hole evaporates via Hawking radiation, this encoded information is slowly and subtly imprinted onto the escaping radiation, preserving it. The non-local connections we've been exploring act as the mechanism that allows this transfer of information, connecting the encoded data on the surface with the particles flying away. So, the information isn't destroyed, it's transmitted via a form of quantum teleportation using the spooky links of entanglement. This resolution suggests that black holes are not the ultimate prisons we once thought, but rather complex quantum objects whose true nature is defined by a non-local, holographic connection between their surface and their interior, revealing a universe where even the most forbidding boundaries are, at a fundamental level, transparent. This idea that the information within a black hole is encoded on its boundary leads us to one of the most profound and radical concepts in all of physics, the holographic principle. It's a theory that suggests our intuitive experience of a three-dimensional universe with its depth, volume, and solidity might be a kind of magnificent illusion. The principle proposes that all the information needed to describe our three-dimensional reality is actually stored on a distant two-dimensional surface. Think of it like a security hologram on your credit card. That tiny, flat, silvery surface contains all the data necessary to project a stunningly detailed three-dimensional image that you can look around. The holographic principle argues that our entire cosmos, with every galaxy, every planet, and every one of us, is that projected image. The real action, the fundamental data of existence, is written on a vast cosmic boundary we cannot see. Now, you might wonder how this could possibly be. How can the rich complexity of a three-dimensional world be completely captured on a two-dimensional screen? It comes down to information. In the 1970s, physicists Jacob Bekenstein and Stephen Hawking discovered that the maximum amount of information that can be contained within any region of space is not proportional to its volume, as you might expect, but to the area of its boundary. This is a revolutionary shift in thinking. For a black hole, the boundary is its event horizon, a spherical surface. The information content of everything that ever fell in is somehow smeared across that surface, with each tiny, fundamental pixel of area, a unit called the Planck area, storing a single bit of information. The holographic principle takes this black hole insight and applies it to the entire universe. It suggests that the spatial volume we inhabit is like the interior of a cosmic black hole, and the information that defines everything within it, the position of every atom, the color of every flower, the memory of every thought, is encoded on a vast, two-dimensional surface at the absolute limits of our observable universe. Our reality, in this view, is a projection from that outer shell. This is where the connection to non-locality becomes breathtakingly clear. If all the information about every location in the universe is stored on a single, connected surface, then every part of our three-dimensional world is inherently linked to every other part through that underlying code. A change in one place isn't an isolated event. It's a modification of the fundamental data on the boundary, which in turn affects the entire projection. It means that what happens here in this room is simultaneously encoded on that distant cosmic film, intertwined with the information for a quasar billions of light years away. The universe isn't just containing non-local connections, it is a non-local structure. The separateness of objects in space is a derived property, an emergent phenomenon from a deeper, unified reality where everything is literally written in the same place. This turns the cosmos into the ultimate hologram, where every fragment, no matter how small, contains, in some sense, the information of the whole. It's a vision of reality that is both deeply strange and profoundly unifying, suggesting that the interconnectedness we see in quantum entanglement is not a minor quirk but a fundamental feature of a cosmic projection, a universe where we are all, quite literally, reading from the same page. From the cosmic scale of black holes and holographic universes, we now turn our gaze inward to the most intimate and mysterious frontier of all, the human mind. For centuries, consciousness has been the ghost in the machine, the elusive inner experience that seems to defy purely physical explanation. How do the electrochemical signals firing in our brains give rise to the rich, unified tapestry of a thought, a memory, or the color red? The dominant view in neuroscience is that the brain is a complex classical computer, and consciousness is an emergent property of its neural network. But this view struggles with what philosopher David Chalmers called the hard problem of consciousness, explaining why and how we have any subjective experience at all. It's one thing to map the brain's wiring, it's another to explain the inner light that shines upon it. This gap has led a number of scientists and thinkers to propose a radical alternative. What if consciousness isn't just a classical computational phenomenon? What if it is fundamentally a quantum process, intimately tied to the non-local, interconnected reality we've been exploring? This idea forms the core of a provocative theory developed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, known as ORCH, which stands for Orchestrated Objective Reduction. Their proposal begins with a surprising location inside our brain cells, structures called microtubules. These are not just simple scaffolding, they are incredibly intricate, lattice-like protein polymers that form the internal skeleton of neurons. For decades, their primary role was thought to be structural, providing shape and acting as railways for transporting molecules, but Hameroff proposed they were much more than that. He saw their intricate architecture as a perfect candidate for a quantum computer. The theory suggests that within these microtubules, electrons can become isolated from their environment, entering a delicate quantum state known as a superposition, where they exist in multiple states at once, just like the famous Schrödinger's cat, both alive and dead. This fragile quantum coherence could be maintained for periods just long enough to perform quantum computations. This is where Penrose's contribution becomes truly revolutionary. He argued that this quantum coherence wouldn't just collapse randomly. Instead, he proposed a process called objective reduction, where the buildup of a quantum superposition in the microtubules eventually reaches a threshold related to the fundamental geometry of spacetime itself. At that moment, the superposition collapses to a single state, and this moment of collapse is not just a physical event, it is, according to the theory, a moment of conscious experience. Each minuscule collapse is a proto-conscious event, and the orchestrated, coordinated collapse of vast networks of these microtubules across the brain gives rise to our stream of conscious awareness. The implications of this are staggering. If consciousness arises from quantum processes within the brain, then it is inherently tied to the non-local fabric of the universe. The entangled states within the microtubules would not be confined to single neurons, but could potentially link different parts of the brain instantaneously, creating the unified, seamless quality of our experience. We don't perceive our vision, hearing, and thoughts as separate data streams. They are woven into a single, coherent whole. Classical physics struggles to explain this binding problem, but quantum non-locality offers a mechanism for instantaneous integration. This framework might even offer a scientific basis for phenomena that have long been relegated to the realm of intuition or gut feelings. Have you ever had a sudden insight, a solution to a problem that seems to pop into your head from nowhere? Or a powerful, unexplainable knowing about a loved one far away? In a classical brain, information processing is local and sequential. But if the brain is tapping into a quantum, non-local network, then information isn't just in the synapses. It could be accessed from a deeper, interconnected level of reality, allowing for a kind of direct knowing that bypasses ordinary sensory input. Our minds, in this view, wouldn't be isolated computational devices locked inside our skulls. They would be more like receivers or amplifiers, tuning into the fundamental non-local field that permeates the cosmos. Of course, it is crucial to state that this theory is highly controversial and is not the mainstream view in neuroscience. Critics point out that the brain is a warm, wet, and noisy place, seemingly the worst possible environment for maintaining the delicate, isolated quantum states necessary for such processes. They argue that any quantum coherence would be almost instantly destroyed by its surroundings, a process known as decoherence. Proponents of the theory counter with evidence that certain biological structures, like those involved in photosynthesis, have been shown to utilize quantum effects even at warm temperatures, and that the ordered structure of microtubules could well be designed to protect against decoherence. The debate is far from settled, but it opens a fascinating doorway. Whether or not the specific arch or model is correct, the broader question remains profoundly compelling. Is our consciousness merely a passenger in a clockwork universe, or is it an active participant, woven from the same non-local threads that stitch the cosmos together? Exploring this possibility doesn't diminish the wonder of the mind. It expands it, connecting the deepest mysteries within us to the grandest mysteries of the universe. Perhaps the most down-to-earth and compelling evidence for this quantum weirdness doesn't come from a physics lab at all, but from the quiet, sun-drenched world of a leaf on a tree. For decades, we assumed that the inner workings of life were purely classical, governed by the familiar bump and jostle rules of chemistry. But it turns out that one of the most fundamental processes for life on Earth, photosynthesis, relies on a stunningly elegant and efficient quantum trick. Inside the light-harvesting complexes of plants, algae, and some bacteria, you'll find a network of molecules called chromophores, which are responsible for capturing packets of light energy or photons. Once a photon is absorbed, it creates an exciton, a particle-like unit of energy. that needs to be transported to a reaction center where it can be converted into chemical fuel for the organism. For a long time, biologists thought this journey was a straightforward, if random, affair. They pictured the exciton like a hot potato, bouncing incoherently from one molecule to the next in a slow, haphazard walk until by chance it stumbled into the reaction center. This model worked, but it had a problem. It wasn't nearly as efficient as the process actually observed in nature. In reality, plants achieve a staggering efficiency rate of over 95% in transferring this energy. A purely random walk would lose far too much energy as waste heat along the way. So, what is the plant's secret? The answer lies in a quantum phenomenon known as coherence. Instead of taking a single, definite path, the exciton enters a state of quantum superposition. It effectively becomes a wave of energy that doesn't exist in one place, but is spread out across all possible pathways through the molecular network simultaneously. It's as if the energy is a traveler who, instead of painstakingly checking one winding road at a time, instantly consults a perfect, non-local map of the entire territory, and then takes the absolute shortest, most efficient route all at once. This process is often described as a quantum walk, and it's profoundly different from a classical random walk. Think of it like the difference between searching for a friend in a vast, unfamiliar city by wandering down random streets versus having an app on your phone that instantly shows you their precise location and the quickest path to get there. The quantum walk is that app. The exciton, in its coherent state, explores the entire molecular landscape in parallel, effectively feeling out all routes at the same time before settling on the most optimal one. This isn't just a minor boost in efficiency. It's a transformative advantage that allows the energy to avoid traps and bottlenecks that would otherwise slow it down and cause it to dissipate. This quantum coherence allows the system to perform a rapid, non-local calculation, finding the global maximum of efficiency in a way that any local, step-by-step process simply cannot. And the most remarkable part of all, this delicate quantum dance isn't happening in the frozen, isolated vacuum of a physicist's experiment. It's occurring in a warm, wet, and chaotic biological environment, precisely the conditions where we once thought quantum effects would be instantly destroyed. The fact that life has not only harnessed these effects but relies on them for its very survival suggests that non-locality is not a fringe curiosity. It is a principle so powerful and useful that evolution, the great tinkerer, discovered it and baked it directly into the fabric of life itself. This discovery fundamentally blurs the line between the quantum and the classical worlds, showing us that the spooky, interconnected realm of the very small is not separate from our lived reality. It is humming quietly and with immense efficiency inside every green leaf that soaks up the sun. So let's take this idea of biological quantum effects out of the leaf and into the sky, because some of the most stunning evidence for nature's use of non-locality involves a feat of navigation that has mystified humans for centuries: the incredible ability of migratory birds to traverse thousands of miles with pinpoint accuracy. Every year, millions of birds, from the tiny reed warbler to the majestic Arctic tern, embark on epic journeys, flying across continents and oceans, often returning to the very same nesting ground with a precision that defies our understanding. For a long time, scientists hypothesized that birds must have some kind of internal biological compass, an ability to sense the Earth's magnetic field. But the real mystery was how. The planet's magnetic field is extraordinarily weak. It's thousands of times weaker than a common refrigerator magnet. Detecting such a faint signal, especially through the thick bone of a skull, seemed almost impossible with any known biological sensor. The leading theory for decades was that birds had tiny particles of magnetite, a magnetic mineral, in their beaks or elsewhere, acting like microscopic compass needles. But while magnetite has been found, its role has been controversial. and it doesn't fully explain the subtlety and sensitivity of the bird's navigational sense, particularly their ability to perceive not just the direction of the magnetic field, but also its inclination, the angle at which the field lines dive into the Earth, which tells them their latitude. This is where the story takes a truly quantum turn. The leading hypothesis now points to a remarkable process happening not in the bird's beak, but right inside its eyes, involving a special light-sensitive protein called cryptochrome. Here's how it's thought to work. When a photon of blue light enters a bird's eye and strikes a cryptochrome molecule, it energizes an electron, kicking it into a higher energy state. This creates a pair of particles with a radical property. They are quantum entangled. For a fleeting moment, these two electrons, though now separated within the molecule, remain a single, unified quantum system. Their spins are linked. Now, the Earth's incredibly weak magnetic field exerts a tiny but measurable force on this entangled electron pair. The field's orientation and strength will influence the relative alignment of their spins. This quantum mechanical interaction is so sensitive that it can be disrupted by the specific angle and intensity of the geomagnetic field. The outcome of this interaction then triggers a chemical reaction within the cryptochrome molecule, which in turn sends a signal to the bird's brain. The crucial point is that this entire mechanism relies on the survival of a delicate quantum state, the entanglement of the electron pair, long enough for the Earth's magnetic field to influence it. The bird isn't seeing the magnetic field as a visible line in the sky. Instead, it's thought that the effect created by this quantum process literally overlays a visual filter onto the bird's field of view, creating patterns of light and dark or even variations in color intensity across its visual landscape. The world might simply look slightly brighter or have a different hue when the bird is facing toward magnetic north compared to when it's facing south. This internal quantum compass provides a constant, real-time heading, painted directly onto the world the bird sees. Imagine having a subtle, intuitive heads-up display permanently projected onto your vision, one that guides you effortlessly across the entire planet. That appears to be the everyday reality for a migratory bird. This isn't just a speculative idea, it's supported by a growing body of evidence. Experiments have shown that birds can only sense the magnetic field in the presence of blue or green light, which is exactly what the cryptochrome mechanism requires. Furthermore, disrupting the birds with a radio frequency noise that is tuned to specifically interfere with the subtle spin transitions of electrons can completely disorient them, scrambling their quantum compass without affecting any other sense. The fact that this biological sensor depends on the coherence of a quantum state in a warm, wet, living cell is a staggering demonstration of evolution's ingenuity. It means that non-locality isn't just a laboratory phenomenon or an exotic process in plants. It is a functional, essential tool for survival in the animal kingdom, a built-in guidance system that uses the instantaneous connections of the quantum world to chart a course across the globe. Now, this profound interconnectedness at the heart of reality isn't just an abstract philosophical wonder. It's the very engine powering one of the most transformative technologies on the horizon. If you want to see non-locality put to work, look no further than the quantum computer. While the classical computers we use every day operate on bits, tiny switches that can be either a 0 or a 1, quantum computers use quantum bits or qubits. And a qubit is a completely different kind of beast. Thanks to the principle of superposition, a qubit isn't confined to being just a 0 or a 1. It can exist in a fluid combination of both states simultaneously, like a coin spinning in mid-air before it lands. This single property already gives a quantum computer a massive advantage, allowing it to explore a vast number of possibilities at the same time. But the real magic, the power multiplier, comes from entanglement. When you entangle multiple qubits together, you don't just have a collection of individual spinning coins. You create a single, unified quantum system where the state of each qubit is intrinsically linked to the state of every other qubit. This non-local connection means that the entire system of qubits can represent a staggering amount of information in a deeply interconnected way. To grasp the scale of this, imagine you have just 300 perfectly entangled qubits. The number of simultaneous states they could represent would be greater than the number of atoms in the entire known universe. A classical computer would need to check each of these possibilities one by one, a task that would take longer than the current age of the cosmos. A quantum computer, by leveraging the non-local links between its qubits, can explore all these pathways in parallel, collapsing almost instantly to the correct answer. This makes them phenomenally powerful for specific, immensely complex problems. Take drug discovery and materials science. To understand how a new molecule might fight a disease or how to design a new super-efficient battery, scientists need to simulate the intricate quantum behavior of atoms and electrons. Classical computers struggle mightily with this. The calculations are so complex they quickly become impossible. But a quantum computer, operating by the same quantum rules as the molecules it's simulating, can model these interactions naturally and with breathtaking speed, potentially leading to cures for diseases or revolutionary new materials. Another field facing a quantum revolution is cryptography. The security of our digital world, from online banking to private messages, often relies on the extreme difficulty of factoring very large numbers into their prime components. For a classical computer, this task becomes exponentially harder as the numbers get bigger, making it a practical safeguard. But a sufficiently powerful quantum computer running a special algorithm could shatter this form of encryption in a matter of hours. This looming threat is already driving the development of quantum-resistant cryptography, while simultaneously, quantum mechanics offers a new form of ultra-secure communication through quantum key distribution, which uses the principles of entanglement to make any eavesdropping attempt instantly detectable. By harnessing the spooky, non-local connections between qubits, quantum computing turns the deepest quirks of our universe into a practical, world-changing tool, promising to solve some of humanity's most enduring challenges by thinking in a way that is fundamentally, profoundly connected. This inherent security of quantum entanglement brings us to one of its most immediate and powerful real-world applications: the creation of communication systems that are, in theory, completely unhackable. This isn't just an incremental improvement on our current digital security. It's a paradigm shift based on the fundamental laws of physics. The technology is called quantum key distribution, or QKD, and it uses the very spooky action that troubled Einstein to create an unparalleled form of encryption. At its heart, QKD isn't about sending the actual message itself through quantum means. Instead, it's about using quantum particles, typically photons, to distribute a secret random key, the code that will be used to encrypt and later decrypt the message. The actual encrypted message can then be sent over a conventional classical channel, like the internet or a fiber optic cable. The revolutionary part is how that secret key is shared. Imagine two people, whom we'll call Alice and Bob, who want to communicate securely. Alice generates a stream of individual photons, each prepared in a specific quantum state that represents a piece of the key, a 0 or a 1. She might prepare these photons using different polarizations, like vertical for 0 and horizontal for 1, or she might use other quantum properties. She then sends this stream of photons to Bob. Now, here is where the magic of quantum mechanics provides the ultimate security guard. One of the core principles of quantum mechanics is that you cannot measure a quantum system without inevitably disturbing it. It's like trying to see the air in a perfectly still room by shining a bright light. The very act of observation creates turbulence. In the context of QKD, if an eavesdropper, let's call her Eve, tries to intercept these photons to read the key, she is forced to measure them. But to measure them, she has to choose a specific basis, a specific angle from which to look. If she guesses the correct basis that Alice used to prepare the photon, she might get away with it for that one bit. But if she guesses wrong, her measurement will randomly change the photon state before it continues on to Bob. This means Eve's snooping introduces errors into the key that Bob receives. After Bob measures all the incoming photons using his own randomly chosen bases, he and Alice then perform a crucial public step. They talk to each other over an open classical channel and compare which bases they used for each photon, but not the actual results they got. They discard all the bits where their bases didn't match. The remaining bits where their bases aligned should form their identical secret key, but now they check for Eve's presence. They take a random sample of these matching bits and publicly announce what the values were. If there is no eavesdropper, their values will match perfectly. However, if Eve has been listening in, her measurements will have caused a statistically significant number of these bits to disagree. Alice and Bob will immediately detect this elevated error rate, and they know their key has been compromised. They simply discard the entire key and start over. The universe itself, through the laws of quantum mechanics, acts as a tamper-evident seal. The security doesn't rely on the computational complexity of a mathematical problem, which a future supercomputer or a clever algorithm might crack. It relies on a fundamental physical law. You cannot copy an unknown quantum state, and you cannot measure it without leaving a trace. This principle is known as the no-cloning theorem, and it is the bedrock of QKD's invulnerability. What's truly breathtaking is the global scale this technology is already achieving. Scientists have successfully demonstrated QKD over hundreds of kilometers using specialized fiber optic networks, and even via satellite, creating entangled links between the ground and space. In one landmark experiment, a Chinese satellite named Mischius sent entangled photons to two ground stations separated by over 1,200 kilometers, establishing a secure quantum key between them. This paves the way for a future quantum internet, a network where sensitive financial, governmental, and personal data can be transmitted with a level of security that is guaranteed by the very fabric of reality, creating a global communication web protected by the instantaneous, non-local handshake of entangled particles. All of this brings us to one of the most thrilling applications of entanglement, a concept that sounds like it's straight out of science fiction, but is very much a reality in labs around the world: quantum teleportation. Now let's clear up a common misconception right away. This isn't the Star Trek kind of teleportation. You won't see a person or even a physical object dematerialize in one place and instantly reappear in another. Instead, quantum teleportation is about moving information, the exact quantum state of a particle, from one location to another. It's the ultimate form of faxing, but for the very identity of a quantum system. The process relies completely on the spooky, non-local handshake of entangled particles and unfolds in a series of fascinating steps. First, you need to create a pair of entangled particles. Let's call them photon A and photon B. You keep photon A with you and you send its entangled partner, photon B, to your friend at a distant location. This establishes a quantum link between the two of you. Now, suppose you have a third photon. Let's call it photon C, which carries the precious quantum state you want to teleport. This could be the specific polarization or spin that encodes a piece of information. Your goal is to make the distant photon B become an exact replica of photon C. Here's the truly clever part. You don't directly send photon C. Instead, you bring photon C together with your half of the entangled pair, photon A, and you perform a special kind of joint measurement on them. This measurement is designed to entangle these two particles, but it has a crucial side effect. The moment you perform this measurement, you destroy the original quantum state of photon C. It's gone forever. This is a fundamental rule. You can't copy a quantum state, so to create a perfect replica elsewhere, you must erase the original. But simultaneously, and here's the non-locality in action, this measurement instantly affects the entire entangled system. Because photon A and photon B were already entangled, the act of measuring A with C causes photon B at the distant location to transform. It doesn't just change randomly, it shifts into a state that is directly related to the original state of photon C. There's one final, crucial step. The specific outcome of your local measurement isn't enough for your friend to know exactly what state their photon B is now in. You have to send them a little bit of extra classical information, just two ordinary bits of data over a standard communication channel, like a radio wave or an internet connection. This message tells your friend what simple correction or rotation they need to apply to their photon B to finalize the process. Once they apply this correction, photon B becomes a perfect, identical copy of the original photon C. The information has been teleported. The quantum state itself wasn't sent through space. It was recreated at the distant location using the non-local bridge of entanglement. The original was destroyed and a perfect duplicate was born light years away, all without the state ever physically traversing the distance between them. This isn't just a laboratory curiosity, it's a cornerstone for the future of quantum networking. Imagine a future quantum internet where quantum computers are linked together, not by sending fragile qubits through fibers where they could be lost, but by teleporting their quantum states directly between nodes, preserving their delicate coherence. It enables a form of distributed quantum computing and provides a fundamentally secure way to transfer information, as any attempt to intercept the process would break the entanglement and be immediately detected. Quantum teleportation turns the most mysterious property of our universe into a powerful, practical tool, demonstrating that the deepest connections can be harnessed to move information itself across the cosmos. Building on the power of teleportation, we can start to envision the full scope of a technology that would bind these capabilities into a global network, the quantum internet. This wouldn't be a simple, faster replacement for the internet we know today. It's something entirely new, a network where the fundamental currency of connection isn't just packets of data, but shared quantum states and entangled particles themselves. Imagine a world where your computer, or more accurately a future quantum computer, isn't an isolated island of calculation, but a node in a vast, synchronized web, all linked by the instantaneous, spooky handshake of entanglement. The security would be woven into its very fabric, not just added on as a layer of software. Sensitive information, from personal medical records to entire national security archives, could be transmitted with a guarantee from the laws of physics that they haven't been intercepted. But the applications go far, far beyond just ultra-secure messaging. One of the most breathtaking possibilities is the creation of a distributed quantum sensing network. Think about how a telescope works today. To see deeper into the universe, we build larger and larger mirrors to collect more light. But there's a physical and economic limit to how big we can build a single instrument. Now imagine if we could turn the entire Earth into one giant telescope. With a quantum internet, this becomes a tangible reality. We could have optical telescopes on different continents, each with their own modest-sized mirrors, but all sharing a common, non-local connection through a web of entangled photons. These separate installations wouldn't just be comparing data after the fact, they would be operating as a single, unified instrument. The entanglement would synchronize their measurements with a precision that is utterly impossible for classical clocks and signals. The effective resolution of this planet-sized virtual telescope would be staggering, allowing us to see the surface of an exoplanet in another solar system with unprecedented clarity, or to peer into the violent accretion disks around supermassive black holes with detail we can only dream of today. The same principle applies to other forms of sensing. A network of quantum gravimeters, devices that measure tiny variations in the Earth's gravitational field, could be entangled to act as one super sensor. This could allow us to map underground aquifers with incredible accuracy, predict volcanic activity by detecting the subtle movement of magma deep beneath the surface, or even locate mineral deposits without any destructive drilling. The non-local links would enable these distributed sensors to cancel out local noise and focus purely on the shared signal they are designed to detect, creating a global consciousness for our planet's subtle physical shifts. This level of synchronization extends to timekeeping as well. Our most accurate atomic clocks are masterpieces of precision, but even they can drift relative to one another. A quantum internet could link these clocks via entanglement, creating a single planet-wide time standard of such stability that it would revolutionize fields like fundamental physics, where testing theories of relativity requires exquisitely precise timing, or global positioning, where the next generation of GPS could achieve centimeter-scale accuracy for everyone. This network would transform our technological capabilities not by making individual devices smarter, but by making them fundamentally and instantly connected, erasing the classical limitations of distance and creating a truly unified global sensorium. This seamless vision of a quantum future, however, runs headlong into one of the most formidable challenges in all of modern science and engineering. While the universe may be fundamentally non-local, our human-made devices exist in a stubbornly local, noisy, and disruptive world. The very property that gives quantum technologies their immense power, the delicate, interconnected state of superposition and entanglement, is also their greatest vulnerability. This fragility is captured by a single critical concept, decoherence. Think of a qubit in a coherent superposition as a perfectly balanced spinning top. It's in a state of pure potential, representing both 0 and 1 simultaneously. But the real world is not a perfect vacuum. It's filled with vibrations, stray electromagnetic fields, and even the slight warmth of the environment itself. These are like random gusts of wind and tiny vibrations on the table. The moment this environmental noise interacts with our spinning quantum top, it knocks it off balance. The superposition collapses and the qubit falls into a definite classical state of either a 0 or a 1. It's no longer a quantum entity exploring multiple paths. It becomes an ordinary switch. This loss of quantum magic, this transition from the weird quantum world to the familiar classical one, is decoherence, and it is the primary enemy of every quantum engineer. The timescale for which a qubit can maintain its coherence is often heartbreakingly short, sometimes lasting only microseconds or even less. For any meaningful quantum calculation or communication to occur, we need to perform thousands or millions of quantum operations within this fleeting window before decoherence destroys the information. It's like trying to perform an incredibly complex symphony, but the musician's instruments spontaneously fall apart if the performance lasts a fraction of a second too long. This is why the most advanced quantum computers today require environments that are among the most extreme ever created by humanity. To protect their fragile qubits from decoherence, they are housed in massive, multi-layered dilution refrigerators that cool the processor down to a temperature just a few thousandths of a degree above absolute zero, colder than the void of deep space. These aren't just ordinary freezers, they are technological marvels designed to eliminate every possible source of thermal vibration. But temperature is only one source of noise. Stray magnetic and electric fields can also disrupt qubits, so they are often shielded with layers of superconducting metal. Even the faintest background radiation from natural minerals in the concrete walls of the building can cause decoherence, leading some laboratories to build shields from specially purified, ancient lead recovered from sunken Roman ships, which is free from the background radiation of modern materials. The quest for isolation is a constant battle against the entire environment. Beyond simply keeping individual qubits coherent, the challenge multiplies exponentially when we try to link them together into large, entangled systems. Creating a handful of entangled qubits is a remarkable feat, but building a useful, fault-tolerant quantum computer may require millions of them, all maintaining their delicate quantum connections with one another. Each additional qubit introduces new pathways for error and decoherence. The complexity of controlling this vast quantum system, of sending precise signals to each qubit without crosstalk disrupting its neighbors, is an engineering nightmare. It's like trying to build a cathedral out of soap bubbles where each new bubble risks popping all the others. This is why scaling up quantum systems is not a straightforward process of just adding more components. It requires entirely new architectures, new materials for building more robust qubits, and revolutionary error correction codes that can detect and fix decoherence as it happens, effectively fighting fire with fire by using small clusters of entangled qubits to protect the quantum information stored in others. The race to harness non-locality is, in many ways, a race against time itself, the pathetically short coherence time of our current technologies. Overcoming this is not merely a technical hurdle, it is a fundamental re-engineering of the environment itself, a monumental effort to create tiny, artificial pockets of the universe where the strange rules of the quantum world can survive long enough to perform the miracles we know they are capable of. So where does all of this leave our most basic understanding of what the world is? For centuries, Western science has been built upon a foundation of materialism and reductionism, a worldview that says the only true reality is physical matter, and that to understand the whole, you simply break it down into its smallest separate parts. We've lived with the comforting assumption of an objective reality out there, a universe that exists independently of us, made of distinct objects following predictable local laws. But the confirmation of non-locality doesn't just add a new fact to this old picture, it shakes that picture to its very foundations, forcing a philosophical earthquake that challenges everything we thought we knew. It suggests that at the most fundamental level, the universe may not be a collection of separate things at all, but a single, unbroken whole, a cosmic tapestry where the threads of existence are woven together in a way that makes the very idea of isolated particles a kind of useful illusion. This shift from a mechanistic, atomistic view to a holistic, integrated one is perhaps the most profound implication of all. Think of the difference between a pile of sand and a living organism. You can study one grain of sand in perfect isolation, and you will understand everything about that grain, but you will learn nothing about the intricate, self-regulating system that is a human body by studying a single cell in a petri dish. The properties of life, consciousness, emotion, thought are emergent properties of the whole, of the connections and relationships between the parts. Non-locality suggests that this principle of wholeness applies not just to biology, but to the fabric of reality itself. The universe appears to operate more like an organism than a machine, with its parts instantly and intimately communicating in a way that transcends the space between them. This directly challenges the materialist assumption that reality is built from bottom-up, local interactions. If two particles light years apart can behave as a single system, then things may not be the primary reality. Relationships and connections might be. Furthermore, this interconnectedness throws a wrench into the gears of strict determinism. The idea that the future is entirely predetermined by the past, like a row of dominoes falling in a perfect chain. In a locally real universe, if you knew the exact position and momentum of every particle, you could, in theory, predict everything that would ever happen. But non-locality, woven together with the inherent randomness of quantum measurement, introduces a fundamental element of unpredictability and perhaps genuine freedom. The universe doesn't seem to pre-decide the outcome of a quantum event until it happens, and when it does, that decision resonates instantly across the entire connected system. It's a cosmos that isn't just unfolding mechanically, but one that is constantly creating itself in a participatory dance between possibility and actuality. A dance where the very act of observation seems to play a crucial role in bringing reality into focus. This leads to the most mind-bending challenge of all, the notion of an objective reality independent of any observer. The classic view is of a universe that would still be there with stars and galaxies, even if every conscious being vanished. But if the properties of particles aren't definite until they are measured, and if that act of measurement is non-locally tied to the entire system, then what does objective even mean? It forces us to consider that reality may not be a pre-recorded movie that we are passively watching, but more like an improvisational play that is being written as it is performed, with our own conscious attention as an integral part of the cast. We are not separate spectators looking at a distant stage. We are actors on the stage, and our presence is influencing the performance. This doesn't mean we create reality out of pure thought, but rather that the universe and the observer are a deeply entangled, inseparable unity. The cosmos is not a cold, empty void sprinkled with isolated objects. It is a vibrant, dynamic, and profoundly interconnected field of existence. A single, breathtaking whole where every part, including us, is fundamentally and instantly linked to the entirety of the rest. Yet this scientific journey into a connected cosmos echoes a wisdom that is ancient and profound. For thousands of years, long before the first quantum experiment, the world's spiritual and mystical traditions have pointed toward a very similar truth, using a different language to describe the same fundamental oneness. In the heart of Hinduism, the concept of Brahman represents the ultimate, unchanging reality, an infinite, impersonal ground of being from which all of existence arises. The famous phrase from the ancient texts, Tat Tvamasi, or Thou art that, is a powerful declaration of this non-local identity. It asserts that the individual soul, the Atman, is not separate from the universal Brahman. The sense of being an isolated self is considered an illusion, a veil of ignorance called Maya. When a meditator experiences a state of samadhi or deep union, the boundaries of the personal self dissolve, revealing a reality where the observer, the process of observation, and the observed are a single, unified field. This is not so different from the quantum perspective, where the act of measurement is inseparable from the system being measured, and entangled particles lose their individual identity to become a single quantum state. Similarly, in Buddhism, the doctrine of dependent origination teaches that all phenomena arise in interdependence with all other phenomena. Nothing possesses an independent, inherent self-existence. A table, for example, cannot be understood in isolation. Its existence depends on the tree it came from, the carpenter who built it, the sunlight that nourished the tree, and the entire cosmic history leading to that moment. This intricate web of mutual causation mirrors the quantum field view, where a particle is understood as a localized excitation of a field that is everywhere, its properties defined in relation to the whole. The Buddhist goal of enlightenment involves a direct, experiential realization of this interconnectedness, seeing through the illusion of a separate self to perceive the seamless flow of a unified existence. This profound resonance between ancient insight and modern physics suggests we are approaching the same mountain from different paths. One uses the rigorous tools of mathematics and experimentation, while the other uses deep contemplation and inner experience, but both are converging on a reality that is holistic, interdependent, and fundamentally non-local. Another fascinating parallel emerges in the theosophical concept of the Akashic Records. This is the idea of a non-physical realm, a cosmic library, or a universal field of information that holds the entire history of the universe, every thought, event, and intention that has ever occurred. It is often described as a kind of indelible memory of the cosmos, a permanent record written on the fabric of reality itself. From a scientific standpoint, this sounds remarkably like a spiritual interpretation of the holographic principle we explored earlier. If our three-dimensional universe is indeed a projection from a two-dimensional boundary where all information is stored, then that boundary effectively acts as a cosmic hard drive containing the complete data of everything that has ever happened within the volume. The Akashic records in this light could be seen as a metaphorical way of describing that same fundamental information field, a non-local repository that transcends space and time, accessible not through a computer, but perhaps through altered states of consciousness where the individual mind momentarily taps into the universal data stream. This isn't to say that science and spirituality are saying the exact same thing. They operate in different domains with different methods and criteria for truth. But the parallels are too striking to ignore. They point toward a unified vision of reality that transcends cultural and historical boundaries. The physicist's description of a universe woven from instantaneous connections finds a powerful echo in the mystic's experience of a boundless, undivided consciousness. Both perspectives challenge the dominant narrative of separation and materialism, inviting us to see the world not as a collection of competing fragments, but as a single, unfolding whole. This confluence of knowledge offers a more complete picture of our place in the cosmos, one where the objective findings of science and the subjective depths of spiritual experience are not enemies, but complementary ways of understanding the profound mystery that we are all a part of. And so we arrive at perhaps the most profound and humbling synthesis of all, a concept that emerges when we weave together the threads of relativity and quantum mechanics. We've explored how non-locality shatters our classical notion of space, revealing an instantaneous connection between distant points. But what if our understanding of time is just as illusory? This is the breathtaking proposition of the block universe theory, a model of reality that comes directly from Einstein's own theory of relativity. In this view, the flow of time is not a fundamental feature of the cosmos, but a kind of persistent, powerful illusion of our conscious minds. The block universe proposes that past, present, and future are not successive states that come in and out of existence. Instead, all of eternity, every event that has ever happened or ever will happen, exists simultaneously, frozen together into a single, four-dimensional structure. Think of it not as a timeline, but as a cosmic loaf of bread. Within this loaf, each slice represents a single moment in time. The moment of your birth is one slice. The moment you are watching this video is another, and the moment of the heat death of the universe is a slice at the far end. From our limited human perspective, we seem to be moving through this loaf, slice by slice, experiencing life as a sequential movie. But from the viewpoint of the cosmos itself, or of a hypothetical observer outside the block, the entire loaf just is. Every moment exists with equal reality, permanently fixed in its relationship to every other moment. This philosophical stance is known as eternalism. It suggests that the dinosaurs are not gone. They are simply located in a different region of the space-time block. The construction of the Great Pyramids is not a completed event lost to history. It is eternally occurring in its designated slice. And your own future, in a very real sense, already exists. This can feel deeply counterintuitive, but it's a direct consequence of Einstein's work, which showed that time is not absolute but is relative to an observer's motion, and is interwoven with the three dimensions of space into a single fabric, space-time. In this fabric, your now is not the same as someone else's now if you are moving relative to each other. There is no universal, privileged present moment that sweeps across the cosmos. Now, let's fuse this with our understanding of non-locality. If the entire universe is a single, static block where every point in space-time is equally real, then the problem of spooky action at a distance begins to transform. The mystery of how two entangled particles can coordinate instantly across space might simply vanish when we reframe the question in terms of the block. In a universe where time is just another dimension, two entangled particles aren't actually separated by a vast distance and time. Their creation, their separation, and their subsequent measurements are all just different locations within the same, unchanging four-dimensional structure. The strong correlation between their measured properties isn't a signal being sent faster than light through space. It's a fundamental, pre-existing geometric fact of the block universe. It's like being puzzled by how 2 points on a printed map are connected. The connection isn't something that happens, it's simply a feature of the map's inherent structure. The points were always linked by the paper they are printed on. In the block universe, the entangled particles were always correlated across their world lines within space-time. Our conscious journey through the block, moment by moment, creates the illusion that one measurement causes the other. But from the God's eye view of the block, it's merely us discovering a correlation that was written into the cosmos from the very beginning. This perspective elegantly dissolves the tension between non-locality and relativity. There is no faster than light influence to explain, because in the timeless geometry of the block, there is no travel happening. The connection is not traversing space, it is a fundamental feature of the underlying space-time geometry itself. The universe isn't performing a magic trick, it is simply revealing its true, four-dimensional nature, a reality where everything is already and forever connected. This vision unifies the grand, deterministic canvas of relativity with the weird, probabilistic world of quantum mechanics, suggesting that what we perceive as random quantum events and instantaneous connections are just the way our linearly processing minds interact with an eternal, interconnected whole. Now, with our most advanced experiments confirming non-locality here on Earth and in near-Earth space, a bold new frontier is opening for physics. We are no longer just asking if this spooky connection is real, we are starting to ask just how far it truly stretches. Does this quantum bond hold firm across the vast, empty gulfs between galaxies, or does it somehow weaken or decay over immense distances? To answer this, scientists are designing the next generation of experiments, cosmic-scale tests that will use the universe itself as their laboratory. One of the most ambitious proposals aims to leverage the most ancient light in the cosmos. The idea is to use distant quasars' incredibly luminous cores of ancient galaxies, powered by supermassive black holes, as cosmic random number generators. Here's how it would work. Researchers would create a pair of entangled photons here on Earth, just as in the aspect experiment. They would then send each photon to a separate telescope, positioned far apart from each other. But instead of using a human-made random number generator to decide how to measure the photons, they would use the light from two different quasars. As a quasar's light arrives at a telescope, its specific wavelength, slightly shifted by the expansion of the universe, would be used to determine the setting of the detector at the very last instant. The sheer distance to these quasars is the key. If two quasars are on opposite sides of the sky, billions of light years from Earth and from each other, their light has been traveling for eons. This means the decision about how to measure one entangled photon would be dictated by a source so distant that, according to classical physics, it would have been impossible for any event at one quasar to have influenced the other quasar since the beginning of time. If, under these conditions, the entangled photons still violate Bell's inequality, it would be the most powerful demonstration ever that non-locality is a truly universal, non-fading property. It would prove that the universe's hidden connections are not just a local phenomenon, but are woven into the fabric of cosmic history itself. Another visionary path involves creating a global or even solar system-wide quantum internet using satellites. We've already taken the first steps with missions like China's Misha satellite, which demonstrated entanglement distribution over 1,200 kilometers between the ground and space. The next logical step is to entangle particles directly between two or more satellites orbiting the Earth, or even stationed at stable points in deeper space. Imagine a future where a constellation of quantum-enabled satellites forms a web around our planet, each one a node capable of sharing entangled photons with its partners. By precisely comparing the measurements of particles separated by tens of thousands of kilometers, we could test the limits of non-locality across distances that are a significant fraction of Earth's own circumference. Pushing even further, we could envision a mission where one satellite is in orbit around Earth and another is placed in orbit around the Moon, or at a Lagrange point in the Earth-Sun system. This would extend the baseline for these tests to hundreds of thousands of kilometers, firmly placing the experiment within the gravitational context of our solar system. The ultimate dream experiment would be to establish an entangled link between a probe sent to a nearby star like Alpha Centauri and a station here in our solar system. While the engineering challenges are staggering, involving unimaginably precise lasers and detectors, the principle is the same. If we could create a pair of entangled particles, send one on a multi-year journey to another star, and then perform measurements, we would be testing quantum connections across interstellar space. A successful result would be truly revolutionary, demonstrating that the strange rules of the quantum world hold sway not just in our laboratories but on a truly galactic stage. Finding that entanglement persists over such cosmic distances would cement the idea that non-locality is a fundamental, unbreakable feature of our universe. However, a failure, a discovery that the correlation weakens or disappears over vast scales, would be equally earth-shattering. It could point toward new physics, perhaps a hint of quantum gravity, suggesting that the structure of space-time itself at cosmological scales somehow disrupts these delicate quantum links. Either outcome would transform our understanding, pushing the boundaries of knowledge by using the immense scale of the cosmos to probe the deepest secrets of the very small. This radical idea of a timeless, block universe where everything is already connected brings us to another compelling, if speculative, possibility, one that has captivated scientists and philosophers alike. If the cosmos operates like a pre-rendered, four-dimensional structure, could it be that our entire reality is, in a very literal sense, a kind of computation? This is the core of the simulation hypothesis, the provocative proposal that what we experience as the universe might not be the base level of reality, but an incredibly advanced simulation running on some sort of cosmic computer. And when we view the phenomenon of non-locality through this lens, its bizarre nature suddenly starts to make a new kind of pragmatic sense. Imagine you are the programmer of this ultimate reality simulation. Your goal is to create a vast, consistent, and immersive virtual world for its inhabitants. One of your biggest challenges is computational resources. If every single particle in your simulation had to constantly send signals to every other particle to update their states, strictly obeying the speed of light limit for every interaction, the processing power required would be astronomical, perhaps even prohibitive. The simulation would be bogged down by an endless torrent of local communications, like a massively multiplayer online game struggling with latency as players spread across the globe try to interact. Now consider a much more elegant and efficient solution, non-locality. Instead of forcing distant parts of your simulation to tediously message each other, you could simply build certain correlations directly into the fundamental code. Entangled particles wouldn't need to communicate because their fates were never independent to begin with. They are linked because they are, at the most basic level, two manifestations of the same underlying variable in your program. When one is measured, the other updates instantly, not because a signal traveled, but because the program simply calls the same piece of data for both. It's a computational shortcut of breathtaking brilliance. Think of it like a well-designed video game. In a complex open-world game, the entire environment isn't rendered in perfect detail all at once. That would overwhelm any processor. Instead, the game engine uses tricks. One common trick is called level of detail, where objects far from the player are rendered with lower resolution textures to save processing power. But an even more fundamental trick is that the game world isn't a physical space, it's a data structure. The location of a tree on a distant mountain isn't determined by sending a message from the mountain to the tree. Both the mountain and the tree are defined by their coordinates in the game's master code. Changing a variable in that code can affect both instantly because they are part of the same integrated system. In this view, non-locality isn't a bug in our reality. It's a feature of optimal simulation design. It allows for the appearance of a vast, spatially separated universe without the crippling computational overhead of enforcing strict local causality for every single quantum event. The spooky action that so troubled Einstein becomes, from a programmer's perspective, a perfectly sensible way to manage resources, ensuring the simulation runs smoothly without unnecessary lag. This perspective also offers a fresh take on the holographic principle we discussed earlier. The idea that all the information in a three-dimensional volume can be stored on a two-dimensional boundary fits perfectly with the simulation hypothesis. In computer science, this is analogous to a fundamental concept. Any three-dimensional scene can be mathematically represented and projected from a two-dimensional array of data. Our three-dimensional universe, with all its rich complexity, could be the projected output, the real-time rendering, of information processed on a two-dimensional surface, the cosmic hard drive. The non-local connections that weave through reality would then be the logical links within that compressed data set, allowing for instantaneous updates across the entire projected scene. This doesn't prove we are in a simulation, of course, but it does provide a powerful and internally consistent framework for understanding why our universe has the strange, non-local properties that it does. It transforms non-locality from a mysterious physical anomaly into a potential signature of an underlying computational architecture, a hint that the laws of physics as we know them might be the high-level user interface for a reality running on a logic we are only just beginning to decipher. Imagine for a moment what becomes possible when humanity not only understands this cosmic interconnectedness intellectually, but begins to live from that understanding. The realization that we are not isolated beings on a lonely rock, but active participants in a seamless, non-local universe could fundamentally reshape our civilization, our relationship with our planet, and our very sense of self. This shift begins with our technology. We've built a world connected by cables and radio waves, where a message to Mars can take up to 20 minutes just for a one-way trip. But if we can harness the non-local links between entangled particles, that paradigm shatters. We could develop a quantum communication network that operates instantaneously across the solar system. Picture a research station on a moon of Jupiter, its scientists working in perfect, real-time collaboration with colleagues on Earth, sharing data and insights with zero latency, as if they were in the same room. This isn't just about faster video calls, it's about creating a truly unified human presence throughout our celestial neighborhood. Interstellar exploration, currently limited by the agonizing delays of light-speed communication, would be transformed. Autonomous probes sent to Alpha Centauri could remain in instant entangled contact with mission control, sending back rich streams of data and receiving complex instructions without the 4-year wait. This would turn a one-way message in a bottle into a genuine, ongoing conversation with the stars, forever altering our relationship with the cosmos from one of lonely observation to one of intimate engagement. This technological leap, however, is merely the external expression of a far more profound internal shift. Grasping our non-local nature could ignite a new ecological and planetary consciousness. For centuries, we have operated under the illusion of separation from the natural world, seeing ourselves as managers or conquerors of a resource to be exploited. But the science now tells a different story, a story where the quantum processes in a leaf, the magnetic navigation of a bird, and the neural networks in our own brains are all tapping into the same fundamental, interconnected field. This knowledge can transform our feeling for the Earth from one of ownership to one of kinship. We would start to see the planet not as a collection of separate ecosystems, but as a single, living, breathing entity, a complex, integrated system of which we are an inseparable part. The pollution we dump into a river wouldn't just be a local problem. it would be recognized as a disruption in the global fluid system of which our own bodies are mostly composed. The destruction of a rainforest would be felt not just as a loss of biodiversity, but as the amputation of a vital organ of our planetary body. This isn't a vague spiritual metaphor, but a scientific imperative born from understanding non-locality. When we truly internalize that we are not on the planet but of the planet, woven from the same quantum fabric, stewardship becomes as natural and necessary as caring for our own health. This expanding sense of connection inevitably reframes our understanding of community and identity. The old tribal divisions of nation, ethnicity, and creed are artifacts of a local, fragmented worldview. They rely on the illusion that we are fundamentally separate from the other. But a non-local reality offers no such refuge for isolation. It suggests that at the most basic level of existence, the boundaries between you and me, and between us and someone on the opposite side of the globe are permeable, if not entirely illusory. This realization has the potential to dissolve the very foundations of conflict, which so often depends on a narrative of us versus them. How do you wage war on a part of yourself? How do you exploit a people you understand to be intrinsically linked to your own existence? The drive for global cooperation would cease to be a political ideal and would become a practical necessity, a direct consequence of understanding the architecture of reality itself. We would approach global challenges from climate change and pandemic response to resource distribution not as competing factions, but as a single planetary organism working to achieve homeostasis. Our economic models could evolve from ones that reward short-sighted extraction to ones that value long-term systemic health, recognizing that the well-being of the individual is inextricably tied to the well-being of the whole. Ultimately, this journey leads to the most personal frontier of all, a shift in human consciousness itself. Throughout history, rare individuals, mystics, sages, and meditators have reported experiences of cosmic unity, a feeling of oneness with all things. Today, modern physics is providing a language and a framework that makes this mystical experience accessible to rational inquiry. It suggests that the feeling of being a separate, isolated self encapsulated within a bag of skin, what we call the ego, might be the grandest illusion of all. Our consciousness may not be generated by the brain in a purely local way, but rather filtered or received by it, tuning into the fundamental non-local field that undergirds everything. This doesn't diminish our individuality, but rather recontextualizes it. We are not drops separate from the ocean. We are distinct, temporary whirlpools in a single, vast sea of consciousness. Embracing this could alleviate the profound existential loneliness that characterizes so much of modern life. The search for meaning would shift from "what can I achieve for myself?" to "how can I, as a unique expression of the cosmos, contribute to the beauty, understanding, and well-being of the whole?" This is the true promise of a non-local cosmos, not just faster gadgets or a cleaner planet, but the dawn of a more mature, compassionate, and unified human existence, where we finally step into our role as the universe becoming aware of itself. And so we reach the end of our exploration, a journey that began with what Einstein called spooky action at a distance and has led us to the edge of a truly holographic, interconnected cosmos. We've witnessed how a simple thought experiment evolved into a testable theorem, how laboratory results confirmed that particles millions of light-years apart could behave as one, and how this principle is not an anomaly but a fundamental feature of reality itself, humming quietly inside every leaf and guiding every migratory bird. This isn't just a story about physics, it's a story about us. It challenges the very core of our lived experience, the feeling that we are separate, isolated minds piloting solitary bodies through a vast and empty space. The science now tells us that this separateness is the illusion, a compelling and persistent one, but an illusion nonetheless. Beneath the surface, the universe operates as an unbroken whole, a seamless tapestry where every thread is intrinsically linked to every other. The implications of this are staggering, rippling out from the quantum lab to touch every aspect of our future. It's the foundation for technologies that will redefine communication and computation, the inspiration for a new ecological consciousness where we see the Earth not as a resource to be used but as a body of which we are a part, and the key to a philosophical shift that could dissolve the tribal boundaries that have divided humanity for millennia. This understanding invites us to see ourselves not as accidental tourists in an indifferent universe, but as active participants in a cosmic process, the universe itself becoming aware, asking questions, and marveling at its own profound and beautiful design. Now we turn this over to you. How does this vision of a connected cosmos change your perspective on your own life, your place in the world, or the nature of reality itself? Share your thoughts and your own mind-expanding questions in the comments below. The conversation is just beginning. And if you want to continue this journey of discovery with us, make sure to subscribe and hit the bell so you don't miss our next exploration into the mysteries that shape our understanding of everything.